So here's our first example. Okay, a 4-meter long ladder is placed against a wall such that the bottom of the ladder is 1 meter away from the wall. So there's our ladder. It's 4 meters long, and this is 1 meter. And the ladder is actually on a bit of a slippery surface. The floor of this is tiles or icy, and it's actually sliding away from the wall at a rate of, so this is sliding, and it's sliding at a rate of 0.05 meters per second. So let's add that in. And my question is, if this is sliding out, how quickly is the top of the ladder sliding down the wall? And specifically at the 10-second mark. So generally, here's what we want to do with these. The first thing is make a picture. The picture is going to help a lot determining our next steps. Second thing, identify the variables that we have and the initial conditions. For instance, in this case we have a picture where this is constant, it's always 4, but these two dimensions are changing. So the h is getting smaller and the x is getting bigger. And not only that, we know a relationship between these three variables because of a formula, and that's what we want to get to as well. So step 3, we want to try and design a formula that will incorporate these variables and these initial conditions. So in this case, the formula is Pythagorean theorem. And I've got some of these initial conditions. One of them was that the x value is increasing at a certain rate, and the rate has to do with time. And so one variable that I have is the change in x over time is equal to 0.05. Another one that I want to find out is how fast is h changing. And I also know some other conditions, like time needs to be 10, and I've got a constant 4 on one side that helps me with the formula. Our next step is to take the derivative of our formula, and you'll notice that we'll start to get some variables that look similar to the ones that we know or want to know. And we're using implicit differentiation, in this case, with respect to t, with respect to time. So we're using implicit differentiation to solve for the unknown variable. In this case, the unknown variable is dh dt. So if I take x squared plus h squared equals 16, and I take the derivative, I get 2x with respect to t, dx dt, plus 2h dh dt is equal to 0. This formula for dh dt gives me 2h dh dt's is equal to negative 2x dx dt's, and dividing by 2h gives me dh dt is equal to negative x over h dx dt. Now to solve this, you notice that I need to know my x and h values, and those are the x and h values at time 10. So at time 10, our picture looks a little bit different. This is 4. This is 1 plus. Now it's been moving for 10 seconds at 0.05 for 10 seconds in this direction. So that gives me a grand total of 1.5 in this direction. And to find h at that time, I'm going to need to use Pythagoras. So it's 16 is equal to, so it's 1.5 squared plus h squared is equal to 4 squared. H squared is equal to 16, take away 2.25. H is equal to the square root of 13.75. And so now I have an x value of 1.5 and an h value of the square root of 13.75. And I know dx dt because it was one of my initial conditions. So I can plug those things in and know that at time 10 I have negative 1.5. This is the square root of 13.75 and the rate is 0.5. A solution. I'll need my calculator for this and I get approximately negative 0.02 meters per second. And that means it's decreasing, it's falling downwards, that's why it's negative, at about 2 centimeters every second. Okay, here's our second example. Paint's pouring into a cylindrical can at a rate of 1/10 of a cubic meter per minute. How fast is the level rising if the base of the can has a radius of 15 centimeters? So again, start by drawing a picture and labeling some things that we know. We know that the radius is 15 centimeters. We know that paint's coming in at a rate of 0.1 cubic meters per minute. And we know that we're looking for how fast this height, so if this is considered the height, how fast is the height changing with time? That's what we want to know. So you should know that the volume of this object is equal to the area of the base, which is a circle, times the height. And you'll notice that the area of the base isn't changing. That's constant. So when we take the derivative with respect to t, we get dv dt. And this constant, we can just substitute the numbers in for. Now you'll notice that meters cubed and centimeters aren't in the same unit, so we do need to convert so they're the same unit. This is the easiest one to convert, so I get 0.15 squared and dh dt. I want to solve for dh dt, so I divide both sides by the pi r squared part, and I get dh dt is equal to whatever the change in volume is compared to pi times 0.15 squared, which is 0.1 divided by pi times 0.15 squared, which gives me approximately 1.4, and the units are meters per minute. And that's not a very effective unit to understand how quickly that's going, especially for a paint can, because it's probably not going to be a meter tall. So it might be better to convert this to a unit that makes more sense, maybe centimeters per second. So once we do that conversion, we see that it goes up about 2.4 centimeters per second, which is pretty quick. Now the whole question changes quite a bit if we're trying to fill a cone, because as we fill the cone, the radius changes. So if you imagine a cone, as you start to fill it up with liquid, the radius of the circle is changing. So now we do need to take that into account with our formula. So let's look at an example with that. So here's our scenario. A cone has a height of 10 meters, and as you're doing this, dissect it, like draw the picture as you're taking information out. So we've got a cone, and the height of this cone is 10 meters, and it's got a radius of 4 meters, and it's being filled with some liquid or sand or water or something, but it's being filled at a rate. So there's your volume, change in volume. And what is the rate of the level rising when it's filled halfway? So again, we're looking for dh dt, and halfway means that when the height is 5 meters. That's what we're looking for. And you'll notice that there's a right-angled triangle inside here, and the right-angled triangle has conditions that one side is 10 and the other one is 4, and you'll notice that a similar triangle appears if you have a height of 5. So because it's similar, this divides by 2, this one also divides by 2. So you know the conditions upon the halfway point, that the radius will be 2 when the height is 5. And that'll be important to know, just like we saw in the very first question. So now we go to volume, and the volume formula for a cone is 1/3 pi r squared h, and we take the derivative with respect to time. 1/3 and pi are constants, but now we have a changing radius, so we now have 2 times the radius times dr dt, and it's a product rule that's actually happening because both of these are variables. So we have that times height, and we have r squared times dh dt. Now we can use that to substitute in some numbers. We are solving for dh dt. But there's actually a problem with this method because we don't know how fast the radius is changing with respect to time. So one thing that we can do to solve this problem that is more helpful is change all of the variables into a single variable. And that is possible to do because we know that there's a relationship between height and radius. In fact, this is your radius, this is your height. You know that the relationship is height compares to 10 as radius compares to 4. And so really our radius is equal to 4 heights over 10. And if we use that instead, so I'm going to go back a step here, then I get a new volume equation where I can substitute in, instead of the r squared, 4h over 10 squared times h. And doing a little bit of manipulation, I get 16h squared over 100 times h, or a formula in terms of only h. So 16h cubed over 100. This is a much easier formula to take the derivative of with respect to time, and it also will only have one variable in it, which is dh dt. So let's do that. dv dt will be equal to, here's all the constant stuff, and then 3h squared times dh dt, and I know that my h value at that time is equal to 5, so I substitute that in, as well as I can substitute in that the volume is changing at a rate of 6. I can manipulate this equation so that I get my change in height, and I get a change in height of about 0.48, and the units are meters per minute. Here's a final example. We've got an observer. They're watching a rocket take off 20 kilometers away. At a certain moment, the angle between the observer and the ground is given, and it's changing. It's increasing at a certain rate. What's the velocity of the rocket at that moment? So here's a picture. There's your observer and the angle they're looking at, the rocket 20 kilometers away, ground level, and the information that we know is that at a certain moment it's an angle of pi over 6, that the angle is changing at a rate of 1.2 radians per minute, and what we want to calculate is how fast the height is increasing. That'll tell us the rocket's speed or velocity. So we need a formula for this information, one that relates an angle to two side measurements, and that would be tangent. Tangent theta is equal to opposite over adjacent, and we can take derivatives of this. The derivative of tan theta with respect to time is secant squared theta times d theta dt. There's your implicit differentiation and chain rule. And on the other side, 1/20th is your constant, dh dt. Now I can substitute in the information that I know. So I'm calculating secant squared of pi over 6 times 1.2 and 1/20th dh dt. Solving for dh dt gives me 20 times 1.2 times whatever the secant of pi over 6 is squared, and calculating that gives me, and in this case that's 18, and the units are Well, it's going up at a certain measurement, kilometers per minute. Now, that's not a very effective unit again, so let's change it to kilometers per hour. It's going to go a lot more kilometers in an hour, and I get 1,080 kilometers per hour. That sounds about right for a rocket.